So the issue is this: you have a patient, real life patient. You have to deliver 100 milliliters of medication through a pump into the IV, and you have to emit it or give it to the patient in 20 minutes. Your pump has a setting on it that gives you the rate of milliliters per hour. The question is, if I have 100 milliliters, I got 20 minutes. I got 20 minutes to put that in there. At what rate do I set the pump in? Okay. I had three nurses sit there, fight with each other and argue with each other for like 10, 15 minutes. And I kept telling them the answer. And they said, no, that can't be right. That can't be right. So they were guessing, 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 guessing. They never stopped to think how to solve that problem, which they could have done it in seconds, 100, and convert your 20 minutes to hours, and you got your rate, and you're done. It should be about 240. Okay. So they never thought about problem solving. So that's my whole function here. Yes, I know I'm not going to make you into chemists. That's okay. All right. If you like chemistry and want to go further, yeah, that's awesome. I'll help you out. But the problem solving is an issue, regardless of what field you're in. Another example, NASA, two groups of scientists, engineers, okay? One working metric units, one working English units. Why, I don't know. They had working two different projects. They had to come together to put this unit together. What's the problem? Well, the problem is one's in metric or one's in English, and that project had a problem with it. Okay. A lot of other, I was in civil engineering as far as um, construction, had a lot of problems there. Okay, so we're working problem solving. Uh, you may input a number wrong on Canvas, and initially I will give you credit, no problem. But think about it. Again, we'll go back to nursing. You're gonna administer 1 cc or 10 cc's. That number is crucial. Be careful, be exact before you hit that submit button. Okay, think about the answer. So anyway, back to where we're going here. We got to work this through and see. We got what happened. Try this again. All right. Back to the problem here. All right. So we have how many pounds are in 248 grams? Well, I'm looking at the situation to identify what I'm looking for. Okay. Unit wise, I'm looking for pounds. Identify what I'm given, and I'm given 249 grams. Okay. And so I got grams, I got to get to pounds. So I need a conversion factor to get me from metric to English units. Okay. So I'm given that 1 pound is equal to 454 grams. And I set that conversion factor up such that I got pounds in the numerator. Okay. And grams in the denominator. Why do I want that? Because when I do the mathematics with respect to the units, this is the basic algebra we're talking about. Okay. My grams cancel out, leaving me the units of pounds, which is what the problem told me I needed to do. So as I follow the units, now I know I can do the mathematics now, because now I plug in 248 divided by 454. My number is 0.546 pounds. Now, the conversion factor 454, that is not an exact number. That's a measurement and has 3 sig figs. But the number we're given is 248 grams. That's a measurement also, not exact. So, but it has three sig figs. So my answer will have to be in 3 significant figures. I understand you can plug it in a calculator and get 10,000 numbers. That would be incorrect. because the whole idea of significant figures, which will continue through the end of the semester, is that you not input, but you present the data no more accurate than the least accurate digits that you're utilizing in your calculation. All right. Here we have another one. Question is, how many inches are in 3.54 times 10 to the negative 3 kilometers? Okay. 3.54 times 10 to the negative 3 kilometers. So I got a very small number. Okay. So here we go again. We got we got to go from inches to kilometers. So I need a conversion factor to get me from metric to inches. And so I set up my system here. So working through, since I start off with units of kilometers, okay, I need a factor to get rid of kilometers. And I know that in 1 kilometer, there are 1,000 meters. So I set it up with meters in the numerator, kilometers in the denominator. Why? Because when I calculate through, my kilometers cancel out. Okay. So at this point, I am in the units of meters. But am I where I need to be? No, I'm not. I need to get to inches. So I need one more factor. So I know that in 1 meter, there's 100 centimeters. So again, I set it up with meters in the denominator because I want meters to cancel, leaving me with centimeters in the numerator. Okay. So at this point of the calculation with the first two factors, I would be simply in units of centimeters. And then again, I go back to the question because the question asked me inches. I need one more factor. And obviously I have the 1 inch is equal to 2.54 centimeters. There, remembering that this factor is an exact number. In fact, all three of my factors here are exact. So they will not play a function with respect to sig figs. I have 3 sig figs to begin with, 3.54. So my answer should be in 3 sig figs, 139 inches. And don't forget the units, okay? I made a mess there of all this. So the point of setting up my this system of these factors is that we're going to use the same system with 3 factors. This is a typical setup and setting up factors in chemical reactions. Because right now we're talking about units, but down the road, we're going to be talking about chemical reactions, reactants, and products and ratios and so forth. And we're going to set it up in the same process. And we're going to continue using the process following the units, okay? Now the math is up to you. Plug it in. You should get up 100. You should get 139 inches in 3.54 times 10 to the negative kilometers. You may need scientific notation to input that number, or you remember I just moved the decimal point over 3 positions to the left to write it longhand and input that. Your calculator will handle it. So if you don't, just put in scientific notation. If you're still having challenges with that, let me know. Maybe after class we can work through your calculators. All right. So another problem here. You're asking, you have a 2-liter soda bottle contains how many quarts? Again, we're still converting, from metric to unit English. Here we're going from metric in liters to quarts. Okay. And so I set up, I am given 2.0 liters. I got to get rid of liters and get into quarts, but I can do it directly. I can, here's the thing here once you become confident in setting up your conversion factors, like the one we just did, if you realize I can set up and make that into one conversion factor, inches in kilometers, I can take that, make one conversion factor. But until such a point that I'm not confident with that, set it up separately, put down the factors that you know and go through the system. That's what we're doing right here. I got 2.0 liters. I know that in 1 liter, there's 100 milliliters. So I can set up my first factor. That gets rid of liters when I do the math, okay? And then I have the conversion factor I'm given at 1/4 is equal to 946 milliliters. So I plug that in. Now I'm in units of quarts. 946 is not an exact number, okay? So it could be a factor with sig figs, but look at what I'm given. I'm given 2.0 liters, which is 2 sig figs. So my answer should have no more than 2 sig figs. The first factor obviously is an exact number, 1,000 milliliters in 1 liter. That's an exact number. So that one, with that one, would be a factor as far as sig figs are concerned. All right, so there's a use the factors that we talked about as far as going from English to metrics. Don't use the other ones because it will give you a different. They have different number of digits, and you're going to end up with different sig figs. Okay. Practice the problems in the worksheets, and get comfortable as much as you can with these type of conversion factors. Okay. So with that being said, we did talk about this earlier in the beginning. We were talking about density. Okay. With this particular section deals with volume by displacement. No big thing here, right? Because what you do, you take a chunk of matter, I put it in a container containing liquids. Guess what? That volume increases, correct? It's because the volume of that chunk of matter is going to displace a volume, and this is what we're talking about. A couple of things. Remember that 1 milliliter is equal to 1 cubic centimeter, or 1 cc. Okay. So if we take a diamond, for example, and we put it in a cylinder, in this case, a graduated cylinder, because it increments, basically a cylinder with increments, so you can measure volume. And we start adding, we put in a graduated cylinder about 20 milliliters of water to begin with, and then we put the diamond in there. Well, obviously, because the diamond has volume, it will displace the volume and bring it up to a new volume, which is 34.7 milliliters. It's like you jumping in the jacuzzi, your volume goes up, right? So what we want to determine is what is the volume of the water? Well, that will be the difference between where the volume ended minus where the volume began. So that'll be 34.7 minus 20 milliliters. That difference is the volume of the diamond, okay? And so that would be that volume. That diamond has a volume of 14.7 milliliters. You can do the same thing with you if if you had a way to make sure that you knew the exact volume of a container, and then you jump in, immerse yourself completely, that new volume that it has now, that difference is your volume. Now, why would I want that? Because we want the volume to calculate eventually density. Okay, density normally, if we have a box, we can measure the density of a box. Very straightforward, length, width, and height. But when you have material that is not easily measured, like the volume of a pencil, your volume, things are irregular shape, we use this technique to determine its volume. Then we take its weight. Guess what? We got the weight, we got the volume, we have density. Okay. All right. So that's what we're doing here. So how do we calculate the volume of a rectangle box? Straightforward, length, width, and height. So in this case, we got a 24 by 11 by 16 centimeter shoebox. Okay. We take its volume, measure it, and that would be 4,200 cubic centimeters. Remember, centimeters times centimeters. The first time, that's centimeter square. The third time, it's centimeter cubed. If we did it a fourth time, it'd be centimeter to the fourth. If we did it 100 times, it'd be centimeter to the 100th. Okay. So don't forget the units. Here we're back to algebra here. So that's 4,200 centimeters. How many milliliters would that be? How many milliliters would 4,200 cubic centimeters be?
4,200 milliliters.
40, exactly, 4,200 milliliters. Okay, how many liters would that be? How many liters with 4,200 cubic
42.
centimeters? Not quite.
4.2.
4.2. Okay. Remember, because we have 4,200 cubic centimeters, 1 centimeter equals 1 milliliter, that equals 4,200 milliliters. And then we know that in 1 milliliter, okay, let me write this out. I'll do it this way. 4,200 cubic centimeters is equal to 4,200 milliliters. And I want to convert that to liters, so I put 1 liter in the numerator, okay? And I know that there are 1,000 milliliters in 1 liter. So by setting up my problem in that manner, my milliliters cancel. I take 4,200 divided by 1,000. I got 4.2 liters. Okay. And so density is, again, this ratio of mass over volume. We just figured out how to calculate the volume by displacement or by direct measurement, depending on the material that we are using or working with. The units of density are mass, which is grams. Okay. Normally that's by default grams over milliliters. The unit in the middle is generally the most used units, grams over milliliters, which is grams over cubic centimeters or grams over, centimeters cubed, either or. CC, same thing. Okay, but the unit in the center is generally the most common units you utilize. You could see things like kilograms over liters or kilograms over kiloliters, any variety combinations. But the most common, again, is grams over milliliters. So think of density as how much matter in the given space. Okay. Now, let me ask you a hypothetical question. We can take a Hershey bar, okay, good old-fashioned Hershey bar. We can measure its volume, okay, length, width, and height, the depth, like we just did with that rectangular box, and we can measure it, weigh it, I should say, so we can get a mass. And so that Hershey bar, who has a mass and it'll have a volume. Now, if I cut that Hershey bar in half, does the density change? If I took that Hershey bar, broke it in half, and I shared the other half with you, would that density of that Hershey
No.
bar? No,
No.
not at all. The mass would change, obviously, but so would the volume. Because you took half of it, now the mass is half. The volume is half of what it was originally, but that ratio remains the same. It's like saying, 5/10 versus 1/2. Different values in numerator denominator, but that ratio remains the same. Okay, now let me ask you another question. Here's a typical question people ask. What weighs more, a ton of steel or a ton of feathers? Well, duh.
They weigh the same.
The same, exactly, right? Okay, now let me ask you this. Who has a greater density, a ton of steel or a ton of feathers?
Ton of steel.
Ton of steel? What if I were to tell you, what's that?
No.
They're both a ton.
You broke up, sorry.
Oh, they both weigh the same.
Yeah, they both weigh the same, but we're talking about density, not the mass.
Oh,
Yeah, so the question again is, who has a greater density? We both agree, everyone agrees, when we just talk about mass, if I have a ton of feathers and a ton of steel, they're both the same, right? No problem there. But let's talk density. Who has a greater density?
I would
The
think
steel,
the steel does.
Okay?
Would depend on what you put it in, wouldn't it?
Could be.
Because technically they have the same mass, but the feathers takes up more of a volume. So you'd have a smaller fraction, therefore smaller density, correct?
Yeah, there we go. Because just like ice, if I take a gram of ice or water, a gram, the moment I freeze that same gram, what I've done is the volume increases. So I change that ratio for water. So that's why ice floats, because the density now is less than one. Okay. So when I look at a ton of steel, one of the properties of metal, a solid, is I cannot crush it any further. The atoms are all as close as they're going to get. But the feathers, I can adjust that volume a little bit more. And when I get that, and if I get those feathers and I crush them in, the volume, my ratio changes and it gets much smaller. The denominator gets small enough so that I could even get the density of the feathers being greater than the steel just by changing the volume. It's analogous to, think of it this way, loaf of bread. We all agree here, loaf of bread is a loaf of bread. We weigh it the same, has the same mass and has the same volume, a given volume, okay? When you first buy it, you can figure out its density. Now take that loaf of bread and do what my boys used to do when they were little, take that bread, squish it, smash it in. What have you done? You have changed the volume, you have decreased the volume, hence the density goes up. So the density of a squished loaf of bread is much higher than the density of a unsquished bread. The mass is the same, but the volume changes, okay? It's a ratio. It's a ratio here that we're dealing with. Okay, so obviously, which state of matter is the most dense? That would be solid, and the least dense, obviously, is gases, okay? Because typical densities of gases are very small numbers, like air and water. Water is our reference point. Normally, it's 1 gram per cubic centimeter or 1 gram per milliliter. At 25 degrees, density does change a little bit with temperature, but we're talking about, we'll say 25 degrees. And that's our reference point, generally, what we think of. So anything greater than 1 will sink in water. Anything less than 1 will float in water. Okay? So density calculations that we're going to do, straightforward density calculations. We got the mass, we got the volume. Bam, we're done. Okay, we can calculate the density. So also remember, we can be doing calculations using density. And density is nothing more than a ratio, okay? Like we've been talking about so far, these conversion factors, like dollars per hour, miles per hour. Density is grams per milliliter. And I can set that ratio up in 2 ways, either with grams in the numerator or invert it and put grams in the denominator. Which one I use depends on the question that I need and what units I need to get rid of, okay? Obviously, if my question says how many grams and I'm using the density of a material, then I'm going to be using the conversion factor in the left because grams is in the numerator. And I'm going to be multiplying that conversion factor in the left by volume in milliliters to get rid of milliliters. And the converse, the opposite for the unit, the way it's set up on the right. Obviously, the one on the right, I'm looking for milliliters given grams, okay? All right, so in this case here, they're asking, here's the question. What is the density of my necklace if 484.56 grams has a volume of 25.64 milliliters? So straightforward, density is mass over volume, okay? So we can divide 484.56 divided by 25.64, keeping track of your sig figs. And your denominator here has 4 sig figs. So using the rules of rounding and so forth, truncated at the 4 sig fig position. Remember about sig figs, add and subtract, think decimal places. Multiply, divide, think sig figs, okay? And don't forget the units, grams per milliliter. So pretty dense necklace. Every 18.9 grams of that necklace has a volume of 1 milliliter, is what that number's telling you. All right. Chloroform. Chloroform is a chemical that used to be used to knock people out when you had to go undergo for an operation. They don't use that anymore. But it has a density of 1.48 grams per milliliter. Okay. So the question ask is, how many grams would 17.54 milliliters of chloroform mass? So if I had 17.5 milliliters of chloroform, how much does it weigh? What is its mass? Is the question. Is what they're essentially asking you. Okay, so we write down what we're given, and that is 17.54 milliliters from the chloroform. The density is given to me, but I need to write it such that grams is in the numerator. Why? Because when I multiply this thing, my milliliters will cancel. And so I set it up properly here, okay? And now it's just a matter of plugging in the numbers in the calculator. And so I have, don't forget, density is a measurement, so it could be a factor with sig figs. It's not, there's no density out there that is an exact measurement. All density values would be measurements. And so it could be a factor in sig figs. So that means that 17.5 milliliters would weigh 25.9 grams. This comes in handy sometimes if you're in the lab and you don't have a balance, but you know the density of a liquid that you're going to use in the reaction. And if I measure out volume 17.5 grams, I know based on the density that 17.5 grams would weigh 25.9 grams. And now I can use that 25.9 grams down the road for further calculations. Okay. Now the other way around, they're asking you how many milliliters would 0.0735 grams of chloroform occupy? So if you were to go to a balance and weigh out 0.0735 grams of chloroform, the question is, what's its volume? Okay. And so we set up the problem again, same way, write down what you're given, okay, and which is 0.0735 grams of chloroform. I'm going to use density again because I need to figure out how many milliliters this material would have. And so this time I write the density of chloroform with milliliters in the numerator. Notice I did not change the factor to 1.48. My suggestion is to leave those numbers, just invert them whole, okay? I know you might be tempted to divide that by 1 to give you that number. That can give you headaches down the road. So just leave the numbers whole. That way there's no question. So just invert them as needed. So in this case, my grams cancel. Okay, which tells me I got it set up properly. I do the math, and therefore 0.0735 grams of chloroform would have a volume of 0.0497 milliliters. Okay. All right. All right. Any questions about the chloroform? But we're gonna talk briefly about energy, and it's pretty self-explanatory, really. All right. We know that hot molecules. Yeah. Somebody had a question. Let me see what it says. Okay. All right. So we're talking about temperature. Okay. And energy. All right. Now, the two are not, they're related, but they're not the same thing. We measure the temperature of matter with a tool, a thermometer, okay? And so if we put energy into the system or take out energy, the effect is that the temperature of that material will either go up or go down, okay? So we're not putting temperature into atom, we're putting energy into the system or taking energy out. And we know that hot molecules move very fast. It makes sense, right? If you're on the beach and you know it's 150 degrees out there on the beach and you got to walk from the beach to go get yourself something to drink, do you think you're going to walk very slow on that hot beach and you're barefoot? No, you're going to run, right? Because it's pretty hot. All right, so hot molecules tend to have a lot of energy and they move around. Okay, they move around. So, whereas compared to cold molecules, they slow down because they have a low amount of energy. Now, temperature we measure with a thermometer, and we have three types of scales that we're going to utilize. Everyone is mostly familiar with Fahrenheit. Okay, it's normally the temperature we use out here. That is the English unit, Fahrenheit. In science, we utilize the Celsius, the scale Celsius. Now, and then there's a third uh, scale called Kelvin. All right. Now, the first two scales go to infinity, either direction, up or down. Okay. These two will go number wise, value wise, will go to infinity. Okay. Kelvin does not. Kelvin, we have absolute zero. There's a point that it stops at zero. Doesn't go into negative Kelvin, stops at zero. That is what we call absolute zero. If for this particular scale, that's where all matter supposedly stops moving. We haven't reached that stage yet. We've gotten pretty close, but we haven't reached. Anyway, Celsius, 100 degrees Celsius represents the boiling point of water, which is in Fahrenheit 212. 0 degrees is the freezing point of water, which is 32 degrees Fahrenheit. Now, to get to Kelvin, we have to go through Celsius. Okay, so if you start off with Fahrenheit in temperature and you need to get to Kelvin, you first have to convert to Celsius, then go to Kelvin. Okay, and the simple, let me clear this up, relationship is this: 273 degrees is added to your degrees in Celsius to give you Kelvin. If you take 100 at 273, guess what you got? 373. If I take 0 and I add 273, I have 273 in Kelvin. Okay. So again, if I'm in Kelvin and I need to get to Fahrenheit, I got to go through Celsius. And if I'm Fahrenheit and I need to get to Kelvin, I got to go through Celsius. Okay. So our conversion factors are given to you. You don't have to memorize them, but they're in the shapes table. Okay, so they're there, but it's given to you here again. So basically Celsius, if I want to get to Celsius and Fahrenheit, I take my temperature Fahrenheit, subtract 32, and I divide by 1.8. All right, or I can take, if I'm in Celsius, I need to go to Fahrenheit. I take my Celsius, multiply by 1.8, and then add 32. It gives me Fahrenheit. And Celsius, to get to Kelvin, I just simply add 273. So check your math here, but if here's 115 degrees Fahrenheit, it's going to represent 46 degrees Celsius and 319 Kelvin. All right. Now, looking at these two beakers here, the question is asking you, which two beakers has the higher temperature? You might be looking at that and saying, well, that's kind of a trick question there, right? Because it got a red stick in there. I'm assuming that's a thermometer. And it's giving you a number there. It says 100 degrees Fahrenheit. So they're both the same. Okay. But the next question says, which has a higher amount of heat? But to answer that, we need to look at the volume. Or you can ask yourself this question. if I have a small pot of water and I'm boiling that for whatever reason, versus a big pot of water and that's boiling to make spaghetti, well, both of them are boiling at 100 degrees Celsius. Okay. But if I had a choice to have one of these spilled on me, which one would you think you would want? The small pot or the big pot? Obviously, the small pot, because even though they both are boiling at the same temperature, because there's less matter in the small pot of water, there's less amount of heat and energy and less destructive. Okay. So that's what the second question is asking you. Temperature both the same. Okay. But A has more water, having more molecules, having more energy, thus more heat. Has anybody from a weather perspective ever heard about El Nino? And if you have, any idea what that may be, other than a little kid?
A hurricane?
Hurricane? No, not quite. In fact, there's two things out there: El Nino and La Nina.
It's the currents that travel from the south to the north from Mexico up across North America, correct?
Yeah, it is current. Yeah, what it is a body of water. It's a body of water that's out in the Pacific. The difference between El Nino and La Nina, obviously, little boy, little girl, but the difference is the quantity of that size of body of water. And that body of water, as we know, if you've ever been in a river and all of a sudden you feel this stream of cold water coming at you, the water is not flowing with the same amount of heat and energy. They have different temperature gradient. So El Nino has a higher warmth, higher temperature gradient, but very small, maybe 1 to 2 degrees. But the mass of water is so large, it has a lot of energy in that short amount of energy, a short amount of degree change differential. But because the mass of water is so large, it has a big effect on the world's weather. And pretty interesting. So that's all it is, just a body of water out there that comes and goes, and it's just a differential of temperature, which has an effect of our weather throughout the world. Now, I may have mentioned this, but we're talking about heat transfer. The thing to remember about energy, okay? Energy always goes from a high state to a low state. We never will see a cup of water sitting on your kitchen top boil on its own, at least not in this universe. Okay. But you'll always will see a cup of hot water sitting on your countertop get cold. Okay, so it always goes from high to low. Now, can you bring it back up to the high temperature stage? Yes, you can, but you got to put energy into it. So think of energy transfer as being on top of a hill. You're going to roll down the hill is much easier than climbing back up the hill. To get back up the hill, you got to put energy into it to get back on top of the hill. All right, so heat transfer, some high temperature, lower temperature. So considering you're taking a cookie stuff coming out of the oven, obviously what's losing heat is the cookie. When you grab it and you burn yourself, that heat transfer to your hand, because your hand is of lower energy state than that hot cookie, and you burn yourself. Okay. And regardless of the temperature, always high to low. If, for example, you are at 0 degrees freezing and you move to an area that is a -15, all right, you are at a higher energy state at 0 than the next state, which is -15, much lower. So your energy loss you're going to lose energy as you go from 0 to -15. On the counter to that, if you're going from 0 to say +15, you're going to gain energy because you are a lower energy state than the +15 temperature. Okay, so that's really the only thing to take away from this. Heat transfers from high to low. And so if you took a piece of metal, placed it in the freezer, the metal is then put in a bucket of hot water. Temperature, what happens to the temperature of the metal? It's gonna increase, right? Because it's gonna gain the heat. And what happens to the temperature of the water? It's going to decrease because it's going to give off the heat to that cold spoon. All right, so if you ever want to cool down your hot cup of water quicker, just stick a cold spoon in there. You'll cool it down real quick. All right. All right, so it's not the quiz, but first exam coming up. So, do the online chapters and so forth, the homework, know your sig figs, practice the conversion factors using temperature and, excuse me, conversion factors using density, for example, and then the temperature conversion problems. Keep track of your sig figs, refresh your sig figs. Remember, add, subtract, think decimal places, multiply, divide, think sig figs. Okay. Obviously, that was for when the last one is don't turn in, we used to do it face to face, but your homework's online. So, all right. Other than that, any questions about these conversion factors? Any of the problems that maybe you want to talk about? If
I have a
not,
question about a problem.
yeah, go right ahead.
It was a problem that was from the homework assignment, chapter 3.
Okay.
I can just tell you it. It's an object weighs 9.0330 grams.
9.330. Okay.
9.0330.
Okay. 9.0330 grams. Okay.
When the object is put in a graduated cylinder that contains 24.9 milliliters of water,
Okay.
the water level rises to 30.2 milliliters, and then they want you to calculate the density of the object.
Okay. All right. Put out for a suggestion there.
It
Okay,
says, figure out the volume.
we
So
gotta.
the volume is a difference between your original starting point and what you ended up with.
Okay, that is correct. Just like we did the example of the necklace. Okay, the necklace was placed in the container to figure out the volume. So you start off at 24.9, right? So and then we ended at 30.2. So we got a difference of that would be, I get 5.3 milliliters of displaced volume. Would you agree?
Yeah.
Okay. Now, the object weighs 9.0330 grams, correct?
Yes.
And the volume that we utilize is 5.3. So to calculate the density would be the mass over volume. Correct? So we will have 9.033 divided by 5.3, and you get this big number. 1.7043396,226, etc., etc. Do you get something like that?
Mm-hmm.
That number?
What?
Okay. So let me share this. Let me share on the face on a whiteboard. Okay, let's share. We'll start whiteboard. And we had tax. And so we started off at 9.0330 grams of what was this object? I don't know, grams, whatever it was. Okay. And then we had a volume of 30.2 milliliters. And we subtracted 24.9 milliliters. And that equals 5.3 milliliters. Everybody agree on that?
Yeah.
Density is equal to mass divided by a volume. Okay, and so we had D is equal to 9.0330 grams divided by 5.3 milliliters. Would that be correct?
Yeah.
Okay. And then when I plug that number in the calculator, guess what I got? All those numbers. Now, would I present all those numbers to my answer?
No.
Where would I truncate? How many sig figs would I? Well, first of all, if you see, the first number was we subtracted, so we're thinking decimal places. So we end up with one decimal place, which is correct, 5.3. Okay. And then we're over here, we're going to take 1, 2, 3, 4, 5 sig figs of 9.03330 grams and divided by number has 2 sig figs. So our answer is to have no more than 2 sig figs. Would you agree?
Yeah.
Where would I truncate it? Where would be the correct answer?
It would be 1.7 grams / milliliters.
You got it, 1.7 grams per milliliters. That should be our answer. Okay.
Yeah, thank you.
Yeah, no problem. Remember, you don't want to present all those numbers. All right. Any other questions? Any other questions or comments? Okay. Well, I'll tell you what, we only got like 15 minutes. I don't want to jump into chapter 4. Why don't you, I'll hang around. If you have any questions, I'll be glad to answer them. And we'll just stop it here, and come Thursday, we'll jump on to chapter 4. Okay? So other than that, I'll see you Thursday, but I'll hang till 2:15 our normal time. Okay? Have a good one. Have a good, safe one.
Professor?
You
Yes.
as well, appreciate it.
Yeah,
I
right.
actually had a question.
Okay,
Yes,
go
it was
ahead.
okay, I can't remember the setup because I just written down my work. We were given 133.5 pounds and then seeing how many grams it would be.
133.5 pounds. Okay. And
Looks
then,
like it for my work.
and then using the conversion factor, let me share this again. Of 4 right here, 1 pound equals 454 grams per 1 pound. Okay. So let me share the whiteboard again, and we'll do that. Okay. So 133.5 pounds is what we're given. And we have a conversion factor of 454 grams per 1 pound. Okay, you see how I set that up? Because we're looking for grams unit wise, are we not?
Yes, we are.
Yes, we are. Okay. So that conversion factor comes from the one we gave you in the Capes table. And so if I look at this, the way I set that up, it's set up properly. If, let's say, for example, I did this and I went this route, and this is why keeping track of your units is so important. But let's say I set it up like this, okay? Can you see where the problem is? Oh, right here. From respect to units, if I set that up with pounds in the numerator, if I look at my units by themselves, I would get pounds. Wouldn't I get pounds square? Pounds
Yes.
times, that would be pounds squared divided by grams, right? So, yeah, so unit wise would just tell me, oh, I'm way on left field, because if I look at just my units, that will be my units, which they don't, that doesn't make sense at all, just from the perspective of the units, right? So that would tell me, that would be my flag that maybe I didn't set up my conversion factor correctly. But if I look at the first one, so this would be a wrong, incorrect setup. So just based on my units. But if I look here, can you see where pounds cancel unit wise?
Yes.
And so now
Yes.
my answer should be, well, 135.5 times 454. Whoop, where'd it go? Okay. Let me do that again. 454 times 133.5. And I think I know what the question is. 133.5. Okay, let me make sure I get the right number here. Okay. Yes. Well, Alex, you got 60, you got the 6,060.9. You might check your calculation here. I plugged mine in twice and I got 60,609. Is there everyone agree on that one?
Yes.
Now the question is, how many sig figs does that have? The answer, the way I wrote it. Wouldn't that be 5 sig figs? 6, the 6 counts, the zeros count. So I got 5 sig figs there, right? That's correct. All right. So, but look at the numbers that I used to do the math. How many sig figs do I have in 133.5?
4.
4, right? And how many do I have in 454? Remember, the conversion factor here is a measurement, it's not exact. So it could play a factor in the sig figs, and in this case it does, because 454
Oh.
has how many sig figs?
Oh.
You got it?
I see now. Yeah, no. I hadn't considered the
Yeah,
conversion
yeah. Remember,
in grams.
yeah,
That's what it was.
right here, the 454 and the 946. Okay, these two conversion factors measurements. Okay, they're not exact numbers, so they could be a factor in your sig figs. In this case, it was the 454. The 1 inch and 254. Okay, I disagree with this, but I have to go with convention and what the department says. They treat that as an exact number. I see it as a measurement like anything else, but it's treated as an exact number. Okay. So the 1 inch,
Okay.
2.54 exact number, not using,
So it would just be the 2 point significant figures.
What's that?
So the
The answer?
so it would only be the 454 grams significant figures, but not the 2.54 centimeters.
You got it. The 254
Okay.
would are exact numbers. The 254 and the 946 are measurements. Okay? So they
Yep.
could be a factor in your calculations where the whiteboard go. And so in this case, that happened exactly in that.
I'll make a note of that for.
Yeah, so our answer should be 3 sig fig. So our answer would be 60600 grams. Would that be correct? With respect to sig
Yes.
fig. With respect to sig figs, remember, I know it may look like a subtle thing, but always keep in mind, your answer should be no more accurate than the least accurate digit. And here, the least accurate digit was the 454. Okay. Because that could have been the other conversion factor. We could have used the volume, but I had a similar situation here where those two conversion factors would be a factor. In other words, if, let's say we were using we could have gone let's say 1, 2, 3, 4, 5 milliliters. And we want to know how many quarts that corresponds to. Okay. Well, oh, if we do the math here, that would be where's my calculator? 1, 2, 3, 4, 5 divided by 946. Check my math. That's what I get in my calculator. Check my math. See, yeah, I should get a number greater than 1. Now, where would I truncate my number? Yeah, at 13049. Exactly. Are you sure? Remember, the 454 in the first 454 grams per pound and the 946 milliliters per quart, those are measurements, but they're not exact numbers. And so using the same reasoning we just did the previous example, what could you say for the example I just created? How many sig figs should our final answer have? Any idea? Oh. Would that be the correct answer? Exactly, 13.0. Yep. Okay, because the
Yes, it would be.
Yep, the 946
Ten-
was
946 is an exact, so significant
you got it.
figures.
So just remember the 454, the 946 are not exact. So if you use them, they would be a factor.
So then would any problem with centimeter
You broke up.
to inch, or sorry, yeah, centimeter to inch with as is?
What would then any centimeter to inch, the sig figs would be dependent on whatever the answer you've given. For example, 12.45 centimeters.
Like this one right here, I have if
Okay, so how many digits would this be? If I have, okay, 12.35 centimeters, I'm converting that to inches. And so my final sig figs would be how many? Because the 254 is treated as exact, what defines my final sig figs would be the number in 12.35. Okay, so it'll be 12.35 divided by 2.54. Okay, this is the number that I calculate right here. Okay. That's what my calculator has. But what governs my sig fig is the 12.35. And that would be, that's correct. The 4.8, excuse me, 86, 862. Where'd it go? Ooh. Okay. Oh. Okay. Because the 254 is a constant number, an exact number, and wouldn't be a factor. Okay. All right. Does that make sense? Okay. So,
yes.
okay.
But I
so-
have an example from the I think it's from the homework that gave me an exact
Okay.
answer that was less than.
Oh, you're breaking up. You want to share your, you want to share your screen? You have it?
Yes, I do have one. It's oh no, not on my screen, but I have it right here. I can just type it out on the chat.
Okay, go ahead. Okay, so you're going from a 19.05
Yes, it was 19.05 centimeters, looking for inches.
inches, right? Okay, so how many, that would be,
Yes.
that would be just like the one we just did, similar. Because notice the 2.35 centimeters, four digits, 4 sig figs, like your 19.05. Okay, let's just write that out. So we got 19.05 centimeters. Okay, we want to go to inches. So inch in denominator, 2.54 centimeters. Okay. Bring the calculator out. We got 19.05 divided by 2.54. Okay. 19.05. Okay. All right. Good choice here. Inches. Yeah, exactly, Alex. And so your calculator output 7.5, right? But your answer has to be with 4 sig figs. So you just have to, like Alex put in his chat, add 2 zeros. And that gives you 4 sig figs. Because remember, the 254 is an exact number and wouldn't be a factor in there. Okay. Hey, he's awake. Does that make sense? Got my little assistant here. You're gonna learn some math, Ruby Rose. Does that make sense?
Partial credit for that question when I'd
Okay.
answered it.
Really?
It might
Well,
be maybe because I didn't completely.
Well, I tell you what, shoot me an email and I go in there and take a
Maybe I
look
didn't
at it.
completely write out for partial. Yes,
Okay.
please do.
Yeah, send me an email so I can go back in there and take a look and see what you did right. But that should be the answer. And if you're typing that in 7.500 and not getting it correct, then Canvas is not doing the right, giving you credit. And I would definitely I will go in there and check everybody's to make sure.
Of course. Thank you.
Yeah, no problem.
All right. Well, then see you,
All right. Any
Professor. I'll go do that right now.
all right, just shoot me an email and I will take a look at it. No
Thanks for the
problem.
examples, by the way. It's a lot more helpful for you to show the example because I got a lot of troubles figuring the sig figs.
Okay.
Hmm.
So the sig figs are trying to figure out as far in the calculation, you mean?
Yeah, like the ones you show, like the questions, like when I was doing the homework, I was a little confused because I didn't fully understand it until like you showed right now. So so I'll be a lot studying until like the exam. So I understand like what I need to do for now.
Okay. All right. Well, that's good.
Thank you for the example. Also have
Yeah,
a good day.
no problem. No problem. Go in there and also look at the worksheets. The worksheets also have
I
some
already did
examples.
those. I already did those like during the weekend, so I have no
Okay.
problem.
All right. Fantastic. Any other questions?
No. Have a good day, by the way.
All right. Thank you, Alex.
Mhm.
All right. All right. Ruby Rose says goodbye. She'll see you guys next time. All right, guys. You guys take it easy. We'll see you Thursday. If Canvas is still acting up, I may have to shift the exam, but we'll see how it goes. I think it's okay right now. I went in there and took a quick look. But anyway, take care. We'll see you guys Thursday. All right. Bye-bye.